Professor Belfrost's science class is back.
Hi, welcome back to my class, and today I'll give you another lesson on chemistry. Let's continue our last lesson on chemistry. We are still in the same chapter of matter, physical and chemical properties, elements, and compounds. And this is the third episode for this chapter. And I think there will be two more videos for this chapter, and we're done and move to the next chapter. Okay, so let's see what we'll discuss today. But before it, let's review a little. Let's recap. I'll give you a summary about our last lesson topic. Okay, so here's this. So substances are identified by their properties as well as by their composition. What is a property? Properties are the characteristics that enable us to distinguish one substance from another. And there are two types of properties, which are physical and chemical properties. All measurable properties of matter fall into two categories: extensive properties and intensive properties. The measure value of an extensive property depends on how much matter is being considered, while the measure value of an intensive property doesn't depend on the amount of matter being considered. First, physical property. What is a physical property? Physical property is a property that can be determined without changing the nature of the substance. Whereas chemical property is a property of matter that describes a substance's ability to participate in chemical reactions, which change one type of matter into another type. Law of, con- law of conservation of energy. What is law of conservation of energy? Law of conservation of energy is just basically state that during any physical or chemical change, the total quantity of energy remains constant, remain the same. Okay. There are long history of atomic theory, and even now, this theory is still evolving, and I'll not explain it again in this review session. And I want you to rewatch if you want to know about the atomic theory. The last lesson, the second video on this chapter. Okay, let's move. The number of protons in nucleus of an atom is its atomic number, which is represented as Z. This is the defining trait of any element. Okay, so its value determines the identity of the atom. Please note this. Okay, and a neutral atom must contain the same number of positive and negative charges, so the number of protons equals the number of electrons. Why don't consider neutron? Because neutron has no charge at all. Okay. The total number of protons and neutrons in an atom is called its mass number, which is represented by the symbol A. And the number of neutrons is therefore the difference between the mass number and the atomic number. A minus Z. Okay? When the numbers of these subatomic particles are not equal, then the atom is said to be electrically charged, and it is called an ion instead of an atom. An atom that gains one or more electrons or lose one or more electrons will exhibit charge. If you lose, then you exhibit a negative charge and called anion. And if we acquire some charge, then it will be positively charged and it will form what's called cation. Okay. Okay, done for the review, and let's start our today's lesson. Now we are explaining about chemical symbol and periodic table later. Okay, so first chemical symbol. Actually, this is a very fundamental thing in chemistry because every element is represented as a chemical symbol to make it easier for you to write on anything. You don't always uh, you should never expect to write the long version of the element that you are trying to explain, right? For example, you are writing tin oxide as tin oxide. You can just shorten it and you can just write SNO2, for example. Okay, it will be much simpler. Okay, so what's a chemical symbol? Chemical symbol is just an abbreviation that we use to indicate an element or an atom of an element. For example, the symbol for mercury is Hg. What is Hg? Hg actually comes from Greek term. If I'm not mistaken, Hg comes from hydrogen. I want you to check it again. Okay, hydrogen. Okay, so we use the same symbol to indicate one atom of mercury, which is microscopic domain, or even to label a container of any atom of the element mercury, which is microscopic domain. What is microscopic and macroscopic domain? Maybe I'll make another video for that in the future, but maybe not in the near time. Okay, I will explaining all about basic things, prerequisite for the chemistry. Okay, so now then, for the first point, move. Some symbols are derived from the common name of the element, others are abbreviation of the names in another language. Most symbols have one or two letters, but three-letter symbols have been used to describe some elements that have atomic numbers greater than 112, yeah, 112, okay. But nowadays, these three character name actually don't exist again because all of the elements with the atomic number greater than 112 actually has been named for some shorter name. Okay, to avoid the confusion with other notation, only the first letter of symbol is capitalized. For example, CO, C capital and O small letter, it is the symbol for the element cobalt. But CO, C capital and O capital too is a notation for the compound carbon monoxide, which contains atom of element carbon, C, and oxygen, O. So traditionally, the discoverer of a new element names the element, but until the name is recognized by the International Union of Pure and Applied Chemistry (IUPAC), the recommended name of the new element is based on the Latin words for its atomic number. For example, element 106 was once called unyl hexium (UNH). Element 107 was once called unyl septium (UNS), and element 108 was called unyl octium (UNO) for several years. These elements are now named after scientists that or sometimes the location where it is found. For example, element 106 is now known as Seabargium in honor of Glenn Seaborg, a Nobel Prize winner, and an element of 109 was named in honor of Lise Meitner, who discovered nuclear fission. Okay, so that's the example for you. The symbol for a specific isotope of any element is written by placing the mass number as a superscript to the left of the element symbol. Please see the figure below. And the atomic number is sometimes written as a subscript preceding the symbol, but since the number defines the element's identity, actually this is not needed and we often omitted it. Okay, please pay attention how we write the mass number as the superscript on the left side, the atomic number as the subscript on the left side, and the charge is as the superscript on the right side. Okay, the right top. Okay, and the charge is only needed if you are representing ion, not atom. But if you only write if you only write an atom symbol, then the charge is not represented. Okay, because atom has no. For example, magnesium exists as a mixture of three isotopes, each with an atomic number of 12 and with mass numbers of 24, 25, and 26 respectively. And these isotopes can be identified as 24 magnesium, 25 magnesium, and 26 magnesium. Okay? And actually it's not read as that. It is read as magnesium 24, magnesium 25, and magnesium 26. Yeah, magnesium 24 means that it has 12 protons and 12 neutrons. Magnesium 25 means it has 13 neutrons, and magnesium 26 actually means that it has 14 neutrons. Note that in addition to standard names and symbol, the isotope of hydrogen are often referred to using common names and accompanying symbol. For example, hydrogen 2, symbolized as stone, is also called deuterium and sometimes symbolized as D capital. Whereas hydrogen 3, symbolized by, yeah, as shown in the slide, is sometimes called tritium, mostly called tritium, and sometimes symbolized as T capital. Because of each proton and each neutron contributes approximately 1 AMU to the mass of an atom, and each electron contributes for less, then the atomic mass of a single atom is approximately equal to its mass number, and it's a whole number. Okay. However, the average masses of atoms of most elements are not whole numbers because most elements exist naturally as mixtures of two or more isotopes. And the mass of an element shown in the periodic table or listed in the table of atom masses is a weighted average mass of all the isotopes present in a naturally occurring sample of that element. And this is equal to the sum of each individual isotope's mass multiplied by its fractional abundance, or the percentage of the composition in the natural existence, okay, natural occurrence, okay. It's written as shown by the formula on the slide. For example, here's an example for you. The element boron is composed of two isotopes. About 90.9% of all boron atoms are boron 10 with a mass of 10.0129 AMU, and the remaining 80.1% are boron 11 with a mass of 11.093 AMU. And the average atomic mass for boron is calculated as shown. Yeah, this is just the sum of the multiplied of the product of each individual isotope mass and its fractional abundance. And then we have the result, which is 10.81 AMU. And this is the average mass of all boron atoms and not the exact mass of each boron atom. This is just the average, okay? Please note it. The occurrence and natural abundance of isotopes can be experimentally determined using an instrument called a mass spectrometer. Mass spectrometry is widely used in chemistry, forensics, medicine, environmental science, and many other fields to analyze and help identify the substance in a sample of material. This instrument is shown in the following figure. If you want to pay attention to it, how it works, you can just browse for another information for another. Okay. In a typical mass spectrometer shown before, the sample is vaporized and exposed to a high-energy electron beam that causes the sample's atom or molecules to become electric charged, typically by losing one or more electrons. And these cations then pass through a variable electromagnetic field that deflects each cation's path to an extent that depends on both its mass and charge. The ions are detected, and a plot of the relative number of ions generated versus their mass-to-charge ratios is made. Okay, we are done with the first part, and now let's move to the chemical formula part. Okay, this is second topic part today. So chemical formula. Okay, first one is molecular formula. It's a molecular formula. A molecular formula is a representation of molecule that uses chemical symbols to indicate the types of atoms, followed by subscripts to show the number of atoms of each type in the molecule. Okay, molecular formulas are also used as abbreviations for the names of compounds. The structural formula for a compound gives the same information as its molecular formula, but also shows how the atoms are connected in the molecule. Please pay attention to the following figure. Okay, so the picture on B, C, D, actually it shows the structural formula. You saw how it is bonded between how the bonding between the atoms C and H are formed. Okay, so the structure formula for methane that's shown before contains symbol for one C atom and four H atoms, indicating the number of atoms in a molecule. The lines represent bonds that hold the atom together. And a ball and stick model shows the geometric arrangement of the atoms with atomic size not to scale, and a space filling model shows the relative size of the atoms. This is respectively the C and D, which is shown in the previous slide. Okay. And although many elements consist of discrete individual atoms, some exist in as molecules that made out of two or more atoms of the element chemically bonded together. For example, most samples of the elements hydrogen, oxygen, and nitrogen are composed of molecules that contain two atoms each, and it is called diatomic molecules, and thus have the molecular formula of H2O2 and N2 respectively. Other elements that commonly found as diatomic molecules are fluorine F2, chlorine Cl2, bromine Br2, and iodine I2. The most common form of the element sulfur is composed of molecules that consist of 8 atoms of sulfur. Its molecular formula is S8. Here is how it looks. Ta-da! I want you to identify which one is which one. Yeah? Which one is space wheel model? Which one is what again? Ball stick model. Okay. And it is important to note that a subscript following a symbol and a number in front of a symbol do not represent the same things. For example, H2 and 2H represent distinctly different species. H2 is a molecular formula and it represents a diatomic molecule of hydrogen consisting of two atoms of the element that are chemically bonded together. While the expression 2H, on the other hand, indicates two separate hydrogen atoms that are not combined as a unit. The expression 2H2, you see, this is the combination, represent two molecules of diatomic hydrogen. Let's see the figure. This is one H atom, two H atom, one H2 molecule, and two H2 molecules. Okay, so compounds are formed when two or more elements chemically combine, resulting in the formation of bonds. For example, hydrogen and oxygen can react to form water. Sodium and chlorine can react to form table salt. We sometimes describe the composition of these compounds with an empirical formula, which indicates the types of atom present and the simplest whole number ratio of the number of atoms or ions in the compound. For example, the titanium dioxide, uh, it has an empirical formula of TiO2, and this identifies the elements titanium Ti and oxygen O as the constituents of titanium dioxide, and it indicates the presence of twice as many atoms of the element oxygen as atoms of the element titanium. As, as have been discussed previously, we can describe a compound with a molecular formula in which the subscript indicate the actual numbers of atoms of each element in the molecule of the compound. Okay, so we have what? First, molecular formula, and second, empirical formula. Okay, so empirical formula is just another simplification of molecular formula by dividing it. I mean, by simplifying, for example, you have the ratio of 2 and 4, we can just simplify it to be the smaller number ratio, is 1 over 2, okay? 1 by 2, okay? In many cases, the molecular formula of a substance is derived from experimental determination of both its empirical formula and its molecular mass. We'll see the example later, okay? Which is the sum of atomic masses for all atoms composing the molecule. For example, it can be determined experimentally that benzene contains two elements, carbon and hydrogen, and that for every carbon atom in benzene there is equal number of hydrogen atoms. Thus, the empirical formula is CH. This is the simplest form. This is not the exact thing that happened. CH is the empirical formula, not the molecular formula. You need to pay attention to this. Be very careful. But an experimental determination of the molecular mass reveals that a molecule of benzene contains 6 carbon atoms and 6 hydrogen atoms. So the molecular formula for this is C6H6, which is shown in the figure. Okay? Pay attention. It has resonance structure. Okay? If we know a compound formula, it can be easily determined empirical formula. Okay, for example, the molecular formula for acetic acid, it is C2H4O2. So you can just know the empirical formula directly, which is CH2O. Okay, I'm sorry, the two must be subscript. Okay. Note that a molecular formula always a whole number multiple of an empirical formula. Also, please note that it may be possible for the same atoms to be arranged in different ways. Okay, compounds with the same molecular formula may have different atom-to-atom bonding and therefore different structure. For example, with the formula C2H4O2, besides being arranged as acetic acid, it can be arranged to form amethyl formate, which is used in manufacturing. Okay, metal formate molecules have one of the oxygen atoms between the two carbon atoms differing from the arrangement in acetic acid molecules. And these two compounds are examples of isomers, compound with the same chemical formula but different molecular structures. Let's see. So pay attention to the following figure. Okay, you can see, right? The arrangement is a little different, and it causes significant difference in the property actually. Okay, so please pay attention. Chemistry is not that easy for you. Sometimes it's unpredictable. Even a little change can cause a huge change in the property, in the real property. I mean. Yeah, okay. So actually, there exist many types of isomers. Acetic acid and methyl formula, which is discussed before, called structure is isomers, which is a compound that the molecule differ in how the atoms are connected to each other. There are also another type, which is called spatial isomers, in which the relative orientation of the atoms in space can be different. For example, the compound carbone, which found in kerosene, spearmint, and mandarin orange peels, consists of two isomers that are mirror image of each other. S plus carbon smells like caraway, and R minus carbon smells like spearmint. See the figure below. Ta-da! So this is the plus carbon, and this is the minus carbon. Okay, one is right hand sided, one is left handed. Okay. Now let's discuss about the periodic table. Oh, actually, I think that this is an enantiomer. We'll discuss enantiomer when we are discussing about organic chemistry. Okay, okay. So now let's discuss about the periodic table. As early chemists worked to purify ores and discover more elements, they realized that various elements could be grouped together by their similar chemical behaviors. One such grouping includes lithium, sodium, and potassium, and these elements are all shiny, conduct heat and electricity well, and have similar chemical properties. The second grouping, for example, for calcium, strontium, and barium, which also are shiny good conductor of heat and electricity and have chemical properties common, but the specific properties of these two groupings are notably different from each other. There's slight difference, okay? Because one is more reactive than the other group. Okay, so yeah, we need some categorization, right? So here the history says. So Dmitry Mendeleev from Russia, 1869, and Latimer in Germany, 1870, independently recognized that there was a periodic relationship among these property of the elements known at the time, and both published tables with the elements arranged according to increasing atomic mass. But yeah, Mendeleev work was recognized more than Mayer's work. Okay. So, for example, the discoveries of gallium and germanium provided great support for Mendeleev's work. Okay, and let's see the periodic table made by Mendeleev in the figure below. You can see it is categorized as groups. I mean, as columns and rows, right? It is. It depends on the similarity of the characteristic. Okay. By the 20th century, it became apparent that the periodic relations involve atomic numbers rather than atomic masses. And the modern statement of the relationship, the periodic law is as follows. The properties of the elements are periodic functions of their atomic numbers. A modern periodic table arranges the elements in increasing order of the atomic numbers and groups atoms with similar properties in the same vertical column. And each box represents an element and contains its atom number, symbol, average atomic mass, and sometimes your name. The elements are arranged in 7 horizontal rows called periods or series. Don't be tricked by two more rows on the at the bottom part of the IUPAC periodic table. It is actually belongs to the 6th and the 7th row, but because we want to make it compact, we just extract it out and put it uh, on its own because they are all having the same properties. Okay, and 18 vertical columns called groups. And groups are labeled at the top of each column. In USA, the labels traditionally were numerals with capital letters, but IUPAC recommends that the number 1 through 18 be used, and these labels are more common. Ah, so I have told you to print your periodic table, right? I want you to take it out, okay? Please take it out because from now on we will use this periodic table quite often, okay? And it is beneficial if you have your periodic table on your table, and when I show something that you feel and you check it directly in your periodic table. I want the newest version of the periodic table, okay? When this video is made, the newest periodic table is as shown in this slide, but I know that the periodic tables will change in the future, so maybe not in your time of watching this video. Okay, so you see that the table to fit on a single page parts of two of the rows. A total of 14 columns are usually written below the main body of the table. As seen is what I think is the lanthanide and actinide. Okay, many elements differ dramatically in their chemical and physical properties, but some elements are similar in their behaviors. For example, many elements appear shiny, malleable, and conduct heat and electricity well, while other elements are not shiny, not malleable, or even not ductile, and are poor conductors of heat and electricity. We can sort the elements into large classes with common properties. Metals, for those with shiny, malleable, and good conductors. Non-metals, elements that are dull, poor conductors, and metalloid, the elements that conduct heat and electricity moderately well and possess some properties of metal and also some non-metals. And the elements can also be classified into two main group elements. In the column labeled 1, 2, and 32, 18, this is the main group 1, and the transition metals starting from 3 to 12. And inner transition metal in the two rows at the bottom of the table. Yeah, the top rows are called lanthanides, and the bottom row elements are called the actinides. Okay. Actually, I don't ask you to memorize all the element, but it is good if you know some because yeah, the most used one. Okay. The elements can be subdivided for specific properties such as the composition of the compound they form. For example, the elements in group 1 form compounds that consist of one atom of the element and one atom of hydrogen. Okay, and these elements except hydrogen are known as alkali metals, and they all have similar chemical properties. The elements in group 2 form compounds consisting of one atom of the elements and two atoms of hydrogen, and these are called the alkaline earth metals, sometimes just earth metals, with similar properties among members of the group. Other groups with specific names are pnictogens. Actually, I rarely say this because it is hard to spell it. Pnictogens, group 15, chalcogens 16, halogens 17, and noble gases 18, or also known as inert gases. Okay, the groups can also be referred to by the first element of the group. For example, the chalcogens can be called the oxygen group or oxygen family. Hydrogen is a unique, non-metallic element with properties similar to both group 1 and group 17 elements. For that reason, hydrogen may be shown at the top of both groups or by itself. See the organization at the table on the next slide. Ta-da! Okay. So elements in groups often behave in a somewhat similar manner. This is partly due to the number of electrons in the outer cell and the similar readiness to bond. Studying the periodic table, you might have noticed something about the atomic masses of some of the elements. Element 43, technetium, element 61, promethium, and most of the elements with atomic number 84, polonium, and higher have their atomic mass given in square brackets. Why? This is done for elements that consist entirely of unstable radioactive isotopes. An average atomic weight cannot be determined for these elements because their radioisotopes may vary significantly in relative abundance depending on the source or may not even exist in nature. And the number in square brackets is the atomic mass number, which is an approximate atomic mass of the most stable isotope of that element that has been researched. Okay, so please note this. Okay, we are done for today's lesson. No assignment for today. Yuppie! And here is a little quote for you today. Okay, so a Turkish proverb once said, no matter how far you have gone on a wrong road, then turn back. Okay, it's never been too late. Just need to realize it and come. I'll open to you every time. Okay, so thanks for watching, and here's what you need to do: subscribe, give a like, comment, and share this video. And I'll be back on every Tuesday and Thursday. So keep watching and be thoughtful. See you.